It's my pleasure to present our first speaker, Ivan Smith, from University of Cambridge. The title of his talk is Stability Conditions in Symplectic Topology.
Okay, so it's a great honor to be here. So this will be a talk about symplectic topology. If you look up the word symplectic in the Oxford English Dictionary, you find that it means twining or plaiting together from the Greek symplectikos, and also copulative in the sense of connecting. It's primarily used in anatomy for a bone in the skull of fishes. And what I hope to show is that symplectic structures also connect different ideas in mathematics, sort of parts of our mental mathematical landscape rather than our actual mathematical hardware. So a symplectic structure on a manifold is a closed, non-degenerate two-form. A two forms a skew-symmetric form on the tangent spaces. A vector space only admits a non-degenerate skew form when it's even-dimensional, so symplectic manifolds are necessarily of even dimension. And for this talk, the most important examples to bear in mind will be smooth, complex algebraic varieties, either affine or projective varieties. In particular, any oriented surface admits symplectic forms. So if I gave you a non-degenerate symmetric bilinear form on the tangent spaces, that would be a Riemannian metric, and that would have curvature as a rather strong local invariant. So for instance, the group of global symmetries of a Riemannian manifold is a finite dimensional group, the isometry group, often a finite group or even trivial. The situation's very different in the symplectic setting. There are no local invariants. Any symplectic manifold near a point locally looks like a ball in Euclidean space equipped with our favorite constant coefficient two form, the one that corresponds to a sum of copies of your standard two-dimensional skew form. And similarly, the group of global symmetries of a symplectic manifold is some infinite dimensional Lie group which acts transitively on points. So before proceeding, again following things that we learned from Emmy Murphy yesterday, the most important submanifolds of symplectic manifolds are not the symplectic submanifolds, but are Lagrangian submanifolds, half-dimensional submanifolds on which the symplectic form vanishes. And the two classes to bear in mind are circles in a surface, a two-form vanishes on a circle, and the real points of any algebraic variety defined by real equations. Something looks locally like Rn in Cn. So since the symplectic symmetry group of a symplectic manifold, the diffeomorphisms that preserve the symplectic form form this vast infinite dimensional group, we usually first focus on its group of components. So we'll let G of x omega be pi naught of, say, the compactly supported symplectomorphisms, and we'll also be interested in a sort of Torelli-type group, I of x omega, the part of the symplectic mapping class group that acts trivially on cohomology. And about a year ago, Nick Sheridan and I proved a theorem saying that in all dimensions at least 4, there's a closed, simply connected symplectic manifold for which this Torelli group is infinitely generated. It surjects onto a countably generated free group. So the aim of this talk is to sort of outline some of the ideas in the proof of that theorem, and in doing so, more generally to tell you, how one might think about these groups G and I. For general reasons, they're countable, but should we imagine that they're rather structured, perhaps finitely presented, arithmetic, hyperbolic, or more pessimistically, might we think there's no structure? Might any countable group be a symplectic mapping class group? And more broadly still, sort of use this theorem to illustrate one of the particular directions in which symplectic topologies evolved in the last few years. Okay, so our simplest symplectic manifolds for today are oriented surfaces. On a surface, a symplectic form is just an area form, and a classical theorem of Moser tells us that any diffeomorphism of a surface with an area form is isotopic to one preserving area. So asking about the symplectic mapping class group of a surface is basically the same as asking about the classical smooth mapping class group of components of orientation-preserving diffeomorphisms. And this is one of the most studied objects in geometry and topology. And that's partly because of its ubiquity. We've introduced it as a differential topological object, but it arises naturally in algebra. It's the outer automorphism group of the fundamental group of the surface. And more relevant to us, it arises naturally in algebraic geometry as the fundamental group, or orbifold fundamental group, of the moduli space of curves. So this is the object whose cohomology was the focus of Rahul Pandya's plenary lecture. And we know many different things about it, and let me emphasize we know things of sort of at least two essentially different flavors. We know algebraic things about it. It is a finitely presented group. That's already not completely obvious. If we look at its cousin, the Torelli group, the part that acts trivially on cohomology, that's not known to be finitely presented, and in fact is known to not be finitely presented. It's an infinitely generated group when G equals 2. And we know explicit finite presentations. We have geometrically meaningful generators. Perhaps the simplest surface diffeomorphisms are Dane twists. There's a little picture of one here. You cut a surface open along a circle, twist by 2 pi and re-glue. If that sounds like it does nothing, you should compare the left and right pictures. But we also know more geometric things about the mapping class group. It's not an arithmetic group, but it has many features in common with arithmetic groups. For instance, it has rigidity properties for actions of lattices. There are strong constraints on homomorphisms between mapping class groups, which tend to be induced by maps of the underlying surfaces. Okay, so these sort of give us some indications of the kinds of things we might want to know or ask about in higher dimensions. Just before proceeding, so this Dane twist, which is supported near a circle in a surface. A circle is the simplest kind of Lagrangian sphere, and it has a cousin in higher dimensions. Whenever I give you a Lagrangian sphere in a symplectic manifold, an open neighborhood of it looks like a piece of its cotangent bundle, and there's again a local compactly supported symplectomorphism called a Dane twist. So at least one thing, a supply of interesting compactly supported symplectomorphisms sort of comes to us rather directly. So how do we learn anything about the symplectic mapping class group? Most of what we know comes from the geometry of families. So let's suppose our symplectic manifold is an algebraic variety. It might be a hypersurface or complete intersection in projective space, and that it moves in some moduli space Mx of varieties. So there's then a universal family, again as discussed by Rahul Pandya, and it's a basic fact that a sort of God-given connection in the total space of this universal family identifies nearby fibers as symplectic manifolds. So they typically won't be the same as algebraic varieties, but they are the same symplectically. And that means that the monodromy of the family induces a representation from the fundamental group of this moduli space Mx into the symplectic mapping class group. And so for instance, these Dane twists, either in two-dimensional surfaces or higher dimensional symplectic manifolds, arise this way as monodromies of the simplest algebraic families, where a family over a disk acquires a single node. And this fact that the two-dimensional mapping class group is the fundamental group of the moduli space of curves is telling us that in the lowest dimension, this kind of classifying monodromy map is an isomorphism. And so that motivates one to ask, more generally, is this an isomorphism, or can we at least characterize, say something about the image of this monodromy? So let's look at one higher degree example. If I take a degree m polynomial, I can look at this affine surface, x squared plus y squared plus p of z is 0. If the polynomial has distinct roots, this is smooth. It inherits a symplectic structure from the standard symplectic structure on C3. And it obviously moves in a family over the space of polynomials with distinct roots, so say configuration space of m points in C. And the fundamental group of configuration space is the braid group. If I take a loop of configurations, I trace out some kind of braid or not. So I get this representation of the braid group into the symplectic mapping class group of my favorite X. It's rather easy to see in this case that if I forget the symplectic structure and just think about this as a family of smooth manifolds, then I lose essentially all of the interesting information. So the monodromy into the smooth mapping class group factors through the finite symmetric group. So this sort of question in blue is really natural only in the setting of symplectic geometry. So in this case, it's known that this map rho is an isomorphism. That has kind of two ingredients. You have to show that it's injective. That amounts to saying that given two braids, I have enough symplectic invariance to distinguish the associated symplectomorphisms. In that case, this is a theorem of Kovanov and Seidel and Thomas. And by now, that's somehow rather classical. We have lots of invariants of symplectic objects. What's much harder is to sort of show or even see why rho should be onto. Because that's really saying that this intrinsically symplectic object, the group G, somehow knows about the particular algebrogeometric origin of this affine surface and this way of presenting it. So in this case, that's a theorem of Wei Wu, fairly recent, but his methods are extraordinarily particular. They wouldn't generalize to a hypersurface if I put some more squared factors there. They don't generalize to essentially any other four manifolds. And so it's this question of how you think about the images of these monodromy maps that I really want to focus on. Before we do that and go to higher dimensional symplectic mapping class groups, we should sort of at least take a nod at the smooth situation. So suppose X is a high dimensional, say, closed manifold, dimension at least 5. So if X is the sphere, its smooth mapping class group pi naught diff X, let's call that gamma of X, this is just the group of exotic spheres. I can use a diffeomorphism of a sphere as a clutching map to glue two n+1 dimensional balls. And this was studied by Kavere and Milner, and it's known to be a finite group. We know a lot about it. But if X is the torus, this mapping class group is known to contain a split summand Z mod 2 to the infinity. In particular, it's infinitely generated. And this sort of gulf between a finite group and a vast group is really something about pi 1. So Sullivan, using methods of surgery theory, showed that for simply connected manifolds, both the smooth mapping class group and its kind of Torelli group, which acts trivially on cohomology, are commensurable with arithmetic groups. That's to say a finite index subgroup is equal to a finite index subgroup in some arithmetic group. And that, for general reasons, means they're finitely presented. It means more than that. They have no non-trivial divisible subgroups. They couldn't contain subgroups like the rationals, for instance. So this gives us some class of sort of universal constraints in the manner of things that we might hope to find in the symplectic setting. This also says, incidentally, that this theorem I started with, joint with Sheridan, is somehow essentially symplectic. I mean, that was about high-dimensional, simply connected symplectic manifolds, and in the smooth setting, the Torelli group can't be infinitely generated. So this fact that this is a really symplectic phenomenon is one of the reasons we're interested. So how do we learn about the smooth mapping class group? I mean, you always learn about a group by making it act on something. Here, it basically acts on cochains on the manifold, Sullivan's minimal model. And of course, when it does that, it acts via the group of homotopy self-equivalences. So why is that a good thing to do? These arithmetic groups arise as automorphisms of cochains, perhaps fixing a collection of cohomology classes. And that really comes down to the Whitney trick. So the Whitney trick lets one cancel intersection points between submanifolds. In this diagram, I have a plane and an arc which meet at 2 points. I pick arcs between them in each of my two submanifolds. That gives me a loop in X. The simple connectivity says I can span that by a disk. The high dimensionality says I can take that disk to be embedded. That's the picture of W. And then a local move lets me push one submanifold off the other. And eventually this lets one simplify the geometric intersections between submanifolds, which is something about smooth topology, to homological algebraic intersections between cohomology classes, which is something well probed by kind of classical algebraic topology. So in 2 dimensions, we also understand the mapping class group by having an act on something. In this case, either the Teichmuller space of curvature -1 metrics, or the sort of more combinatorial complex of curves. So in one formulation, this is just a graph whose vertices are simple closed curves up to isotopy, and where we put an edge in if we can disjoin the 2 curves, one from another. So that sounds rather simplistic, but as Thurston famously illustrated, a general simple closed curve on a surface is a rather complicated thing. It winds around in a complicated way. And we're not now in high dimensions, and we're not now in a simply connected setting. So this question of disjoining is something about geometric intersection numbers, which goes beyond homological intersection theory. And that's key. And in some sense, one of the most fundamental theorems in 2-dimensional topology is that Teichmuller space is contractible, or this complex of curves is hyperbolic in the sense of Gromov. And much of what we know about the 2-dimensional mapping class group can be traced back to those facts. And so, for instance, if you think about a finite subgroup and you're in a sort of reasonably negatively curved space, well, finite sets have unique centers of mass. That leads to fixed point theorems. That's somehow the idea of the proof of the Nielsen realization theorem, which says finite subgroups of the mapping class group are groups of hyperbolic isometries, and then easy hyperbolic geometry gives one a bound on the order of torsion elements. So in high dimensions, we can imitate the construction of this complex of curves, but we don't get very far. So we can form a graph whose vertices are Lagrangian spheres up to Lagrangian isotopy, and where we put in an edge if we can disjoin the spheres by isotopy, and the symplectic mapping class group acts by simplicial automorphisms. But we just don't understand these graphs well enough for them to be really useful. So even if we think about surfaces in CP3, it's easy that the projective plane has no Lagrangian sphere. The quadric surface does have one, and it's a deep theorem of Hind that there's only one up to isotopy. And already at the cubic surface, we don't know how to classify Lagrangian spheres. We don't know that the group G acts on this graph with finitely many orbits of vertices. So to proceed, we need some more technology. And the technology that's used is Fleur Theory. So here is an attempt to present 25 years of fairly technical developments in symplectic topology in one slide. Fleur Theory associates to a pair of, let's say, closed and oriented Lagrangian submanifolds vector space. It's the cohomology of a cochain complex. Let's recall that Lagrangians are half-dimensional submanifolds, so if I wiggle them a little bit, I might expect them to meet in finitely many points transversely, and the cochain complex we look at is generated over some field K by the finite set of intersection points. But the differential in this cochain complex counts solutions to a certain PDE. That PDE concerns maps of the 2-dimensional disk to my symplectic manifold, which satisfy the D-bar equation. So I pick as a background piece of data a complex structure on X. Then I can make sense of which disks are holomorphic. And as in this top picture, I want to define a differential. A generating cochain is an intersection point P. Its differential will be a linear combination of other intersection points Q. To tell you the coefficient of some particular Q, I have to give you a number. And that number will be the number of maps U from the disk to X, which take 2 boundary arcs of the disk to my chosen Lagrangians L and K, take 2 boundary marked points, here plus and minus I, to my chosen intersection points, P and Q, and which satisfy the Cauchy-Riemann equations, which is a nonlinear PDE. And there's obviously a lot of analysis in the background to do with the ellipticity of the Cauchy-Riemann equation to say that it makes sense to count these. There are delicate compactness issues. Setting up this theory takes a vast amount of work, none of which I will do justice to. But we see a couple of things immediately. So the Euler characteristic of this cochain complex, which we can read off just from the cochain group, is the classical homological intersection of the homology classes of L and K. So this is some kind of refined version of intersection theory. And you should think of it in terms of the way we applied the Whitney trick to simplify smooth topology, as saying that here we're only allowed to cancel intersections between Lagrangian submanifolds if we can cancel them by a Whitney trick along a holomorphic disk. And what comes out is a sort of Lagrangian isotopy invariant which refines intersection theory. The naive geometric intersection of L and K wouldn't be invariant under Lagrangian isotopy, and the homological intersection is invariant under all smooth isotopy, and this somehow helpfully mediates between the two. A Lagrangian L is never meeting itself in finitely many points, but one can make sense of the theory in that case, and Fleur cohomology is a kind of corrected version of the ordinary cohomology in the sense that there's a spectral sequence from the cohomology of L to Fleur cohomology, and the differentials involve holomorphic disks with boundary on L. Okay, so finding solutions to a PDE is hard, which means that at first sight, this theory looks, completely uncomputable. But if you learn singular or de Rham cohomology, then at first sight, those theories are also completely uncomputable. They're rendered computable by virtue of the Eilenberg-Steenrod axioms, in other words, by their internal algebraic structure. And the same is true here. So the first piece of structure in classical cohomology is the cup product. And there's a product structure in Lagrangian Fleur cohomology. So if I have three Lagrangians, L, M, and N, and I give you intersection points of L and M and N, and I want to multiply them, that again will be some linear combination of intersection points of L and N. And so I'll tell you what the product is by giving you a numerical coefficient for each possible output intersection, and that now counts sort of holomorphic triangles, as in this schematic. So again, maps from a disk with three boundary arcs. The arcs map to my chosen Lagrangians, and the map of the disk should be holomorphic, should satisfy this rigidifying PDE. And if L equals M equals N, this is a corrected version of the classical cup product, which takes account of holomorphic disks with boundary on L. So the two pictures show we're counting bigons and we're counting triangles. It's not a wild stretch of the imagination to think that one should also count squares and pentagons and hexagons and the like. There's an essential difference, which is that I defined this triangle product by giving you intersection points, which are not Fleur cohomology classes, they're Fleur cochains, and one has to check that this product descends to cohomology. And for the operations associated to polygons with more sides, that ceases to be true. They're more like Massey product information. They depend on choices and they don't descend to cohomology. That somehow geometrically comes because a disk with more boundary marked points has its own conformal parameters. But nonetheless, this chain level structure exists, and the output is a category associated to your symplectic manifold. The objects are Lagrangian submanifolds. The morphisms between two Lagrangians are this Fleur cohomology group. Composition of morphisms is this triangle product. And then there's a lot of additional chain level structure. So in classical cohomology, along with products, we also have exact sequences, Meyer-Vittorus type sequences. And again, those have an analog in Fleur theory. So there are distinguished triangles, triples of Lagrangian submanifolds, L1, L2, L3, with the property that if I take morphisms to a fourth Lagrangian, that's to say I consider the groups HF L1K, HF L2K, and HF L3K, then those groups fit into a long exact sequence. So this category actually has the structure that goes by the name of a triangulated category. It has certain distinguished triangles of objects which are coupled to the existence of long exact sequences of morphism groups. And in some sense, the point of having all of this algebraic structure is that everywhere in mathematics you encounter long exact sequences, there are triangulated categories lurking in the background, be they exact sequences of modules over a ring or exact sequences of sheaves on a variety. So this is a structure that occurs elsewhere, and that means that people in other parts of mathematics have developed technology to think about triangulated categories, and that's technology that we can now try and import into symplectic topology. And the particular piece of technology I want to import, it's about 15 years old now, it's due to Tom Bridgeland, and it goes by the name of stability conditions. So Bridgeland associates to a triangulated category a kind of Teichmuller space, a complex manifold, called the space of stability conditions. So a stability condition has two pieces of data. The first is a map Z from the Grothendieck group of the category to C. So the Grothendieck group K of D is just the free abelian group on the objects of the category, but we divide by relations coming from these distinguished triangles of objects. When three objects form a triangle, we put their alternating sum to 0. So that should be reminiscent of something like an Euler characteristic. And then the other piece of data is a massive collection of subcategories, one for every real number phi. These are called p phi. It's tied to this map Z because if I take an object in one of the subcategories, Z should take it to a complex number of slope phi. So the elements of p phi are said to be phi stable. And every object in the category should somehow be built out of these subcategories in the sense that an object E should have a collection of sort of sub-objects, things that map to it, E1 up to EK minus 1, such that the mapping cones of these maps from EI to EI plus 1 give us new objects AI which belong to these subcategories. Okay? And Bridgeland's theorem is that if you forget all of this data to do with the P's and you just remember Z, that's a map from an abelian group to C, then that's a local isomorphism. So this space is locally modeled on a complex vector space and is hence a complex manifold. Okay, so the data of a stability condition is reasonably impenetrable at first sight. If you're an algebraic geometer who knows the theory of vector bundles and Harder-Narasimhan filtrations, you'll have a context for it. I'm not one such person. But nonetheless, the definition was actually inspired by symplectic topology. So the motivation for this definition is in some sense the following. Suppose I give you a symplectic manifold, which is a Calabi-Yau algebraic variety. So it's a complex Kähler manifold of dimension n, which admits a nowhere zero holomorphic n form. Well, then I can associate to every Lagrangian L a complex number by integrating this holomorphic form over L. So that gives me a number for every object of the Fukaya category of X. And if I give you a general Lagrangian, I can look at two things. I can restrict the holomorphic form to L, and I could also take its Riemannian volume form, because I now have both a symplectic structure and a complex structure in play, so I have a Kähler structure. And these will differ by some function, so there's a sort of distinguished class of so-called special Lagrangian submanifolds in which this function is just a constant phase. So here phase is somehow circle valued, there's a way of making it real valued, I'll elide that for now, but I get these special Lagrangian submanifolds of phase phi. And there's a much studied geometric flow in general in Riemannian geometry, but in particular in symplectic geometry, called mean curvature flow. I evolve a submanifold by its mean curvature to try and make it minimal, volume minimizing. That preserves the Lagrangian condition, and it acts on this phase function by the Laplace operator. So the phase of a Lagrangian evolves according to the Laplace equation. So if this flow existed for all time, I would expect to flow my Lagrangian to something in which its phase was harmonic, so if L is closed, constant, in other words, to flow to one of these special Lagrangians. This flow is extremely difficult. Actually, we expect it to develop finite time singularities. We know it develops finite time singularities. We hope one could continue past them. Very little is known. But there's a sort of motivating picture in which a choice of pair of complex structure J and nowhere zero holomorphic N form omega on a Calabi-Yau manifold should give me one of these stability conditions in which this data Z is given by integrating omega. The data of these AJs are the special Lagrangians which show up when I flow by mean curvature flow. And then there's some way, supposedly, that nobody understands at all of assembling these. But we have this sort of meta-conjecture, this space of pairs, J omega, injects into the space of stability conditions, maybe more properly the universal cover of this space of pairs, J and omega. Okay, and there's a central conjecture in this subject, which is that spaces of stability conditions should be contractible. Okay, so let's suppose, for instance, this Grothendieck group K is just a finite rank abelian group. So then I said that the space of stability conditions is modeled on Hom from K to C. So that just becomes C to the D. I have a D-dimensional complex manifold. This is intrinsic to the category D, so the natural symmetry group of the category, the group of autoequivalences, acts on this. Of course, making an interesting group act on a space, if it acts sufficiently badly, is not interesting. But it's I think, quite remarkable fact here that at least if I kill the generic stabilizer, I throw away things that do nothing, this autoequivalence group acts discretely and with finite stabilizers. So stab mod aut is actually a complex orbifold, and in all known examples, it's an orbifold K pi 1. So you should think of this theory as an attempt to build a model for the classifying space of this natural group, the symmetry group of the category, out of the data of the category itself. And there are finitely presented groups which can't act effectively on any finite dimensional contractible manifold. For instance, Thompson's group F has infinite rational virtual cohomological dimension. So if we knew this sort of conjecture in some generality, we might believe that symplectic mapping class groups of sort of Calabi-Yau manifolds satisfy some sort of universal constraints, a bit like the fact that there were universal constraints on things that could be high-dimensional smooth mapping class groups. My time now says check TX's input signal, which I will take as discouraging but not yet lethal. Okay, so we have some strategy now to try and think about, the symplectic mapping class group, not in terms of distinguishing mapping classes via invariance, but actually having it act on something, okay? So suppose I have a symplectic manifold which is a Calabi-Yau manifold, and it moves in some moduli space M of X. I have a monodromy representation from pi 1 of moduli space to the symplectic mapping class group. The symplectic mapping class group acts by autoequivalences of the Fukaya category because it's an object of symplectic geometry. The autoequivalence group of the category is acting by deck transformations on the space of stability conditions. So if I knew the space of stability conditions was contractible, or at least simply connected, and I could relate stab mod aut to the classical algebrogeometric moduli space, then I would end up building a map from pi 1 of mx to pi 1 of mx, which, in any just world will be the identity. And that would show that the symplectic mapping class group is the fundamental group of the moduli space, semi-direct product, some kind of invisible piece, some sort of negligible piece, negligible because my understanding of it is negligible, which is the part of the symplectic mapping class group that acts trivially on the Fukaya category. This is fantastic. I now have 45 minutes. Game on. Okay, so you should not expect this to work in any kind of generality. Right? I mean, when this works, we're back in this situation that says that the symplectic topology of X somehow knows the algebrogeometric moduli space. This is not a kind of universal template, the astonishing thing is that there are cases where it works. So this does work in the case of that family of affine surfaces X that I talked about earlier. But it works more generally, it works for their higher dimensional cousins, and it's a version of this that works and enables us to prove the theorem I mentioned with Sheridan. Okay, so to use this idea, one has to be able to compute a space of stability conditions. There's a number of computations in the literature, of which the most beautiful is the theorem of Arendt, Bayer, and Tom Bridgeland, and it applies in a slightly different setting. So it starts with a complex K3 surface of Picard rank 1, and it computes the space of stability conditions on its derived category of coherent sheaves. And it proves that it's contractible, or at least has an Ortek invariant contractible component. So we say a symplectic manifold is homologically mirror to Y if the Fukaya category of X, this object of symplectic geometry, is equivalent to the derived category of sheaves of Y. So how should you think about this? Y is a moduli space of points on Y. And a point on Y is the same data as the skyscraper sheaf of the point. So Y is a moduli space of skyscraper sheaves on Y. And if this equivalence holds, those skyscraper sheaves become objects of the Fukaya category, so I should think of Y as a moduli space of Lagrangians in X. And morphisms in the derived category are given by X'd groups. The X's of a skyscraper sheaf with itself are an exterior algebra. They're the cohomology of a torus. So we might hope to build Y as a moduli space of Lagrangian tori in X. And this has driven a vast amount of exciting work, but we don't actually manage to prove mirror symmetry that way. The current proofs are somehow difficult and ad hoc and follow in the lines of beautiful work of Seidel and Sheridan. One delicacy is that Y turns out to be defined over some kind of non-Archimedean field. But putting that aside, let's suppose that one has found a homological mirror to this Picard rank 1 K3 surface. We do that. It turns out to be a certain symplectic K3 surface. Then the Bio Bridgeland Theorem identifies for you sort of stab mod ort by virtue of identifying it on the algebro-geometric side. In this case, it turns out to be just what it's meant to be, the moduli space of complex structures and nowhere zero holomorphic volume forms. The fact that Y is Picard rank 1 turns out to mean that the relevant space of complex structures is one-dimensional, so it's some modular curve. A choice of a holomorphic volume form is just a choice in C star. So one finds that there's some C star bundle over a modular curve whose fundamental group is the autoequivalence group of this category. We were interested in the part of the symplectic mapping class group that acted trivially on cohomology. That's like the autoequivalences that act trivially on Hochschild cohomology. That corresponds to a certain covering of this space, and one works out that covering, and it's an infinitely punctured upper half plane. And then you run this program from the previous slide, sort of think about the monodromy map composed with the action of equivalences, and indeed you find that this symplectic Torelli group for these K3 surfaces, or products of these K3 surfaces with themselves, surjects onto a countably generated free group. So that's sort of, broadly speaking, how this theorem with Sheridan's proved. One thing I want to emphasize is that you can't start this program until you have Fleur theory developed to the point that you have this Fukaya category as a triangulated A-infinity category. So there's a lot of analysis at the heart of Fleur theory. That's extremely important, and I haven't talked about it. But for recognizing the structure you get elsewhere in mathematics, you really need all of the algebra that comes on top of that mathematics. And I think that's one of the appealing things about this. I'd like to say something about the Bio Bridgeland Theorem, which is in many ways the sort of heavy lifting in this work, the construction of the Fukaya category aside. So they use a geometric flow, but it's a flow on the space of stability conditions. So they take the skyscraper sheaf of a point. If I give you a stability condition, then from our axioms, that should have certain stable factors, these AJs, which came with phases. They had certain slopes. And they look at the difference between the maximum and minimum of these slopes and try and write down a flow which lets one decrease that until eventually it becomes 0 and the skyscraper sheaf becomes stable. And then they analyze by hand stability conditions where that property is true, where skyscrapers are stable. So in our sort of, heuristic relation for mirror symmetry, the skyscraper sheaf corresponded to a Lagrangian torus, and this argument is saying you fix the Lagrangian torus and you flow in the space of pairs J and omega, that's the space of stability conditions, to make that torus special, which is very different to what we do in classical mean curvature flow, where we fix J and omega and we try and flow the Lagrangian, the object, to make it special. And this is probably something from which we could learn something in geometric analysis. Okay, so there are not many cases in which we understand stability conditions, but there are some. One large class I just want to talk about briefly as a digression, as a sort of apology for using this term, which Bridgeland doesn't, that the space of stability conditions is like a Teichmüller space, because it establishes a connection to classical Teichmüller theory. So if I give you a quiver, that's to say an oriented graph, together with a potential, that's a formal combination of cycles, there's a method due to Ginzburg to build from that one of these triangulated A infinity categories, and that then has a space of stability conditions. And this is a class that we understand reasonably well. And one source of quivers with potential comes from triangulations of actual surfaces. So in this picture, there are some dotted triangles in the faint background. That's a triangulation of my surface. And in the middle of each triangle, I've inscribed a clockwise triangle of arrows. And that gives rise to a directed graph, and I see two obvious systems of cycles, the little sort of clockwise arrows I just put in that form these triangles, but there are also some sort of anti-clockwise larger polygons that you also see in the picture, sort of going the wrong way around these triangles. Okay, so this gives me equivalent potential. That defines a category. One can show the category doesn't depend on the choice of triangulation. And it's a fact that this is essentially the Fukaya category of a certain Calabi-Yau threefold which fibers over the original surface sigma with certain singular fibers. And a few years ago, Tom Bridgeland and I proved that in this case, stab mod ought is again what it ought to be. It's a space of quadratic differentials, in fact, meromorphic quadratic differentials. And in this dictionary, a choice of quadratic differential on a surface gives rise to a flat metric. Much studied in Teichmüller theory are, say, the saddle connections, the finite length straight geodesics for that flat metric. Those biject exactly with, on the one hand, special Lagrangian three spheres in this threefold, and on the other hand, stable objects, the objects of these rather simple categories P phi for our stability condition, where the slope of the saddle connection is the sort of phase of the stable object. And so there's a huge amount known about sort of growth rates for saddle connections, about many interesting developments in Teichmüller theory over the last 15, 20 years, partly related to billiards, partly related to other things, study these spaces of quadratic differentials, and many of those questions can now be asked somehow more generally for these Teichmüller spaces associated to other triangulated categories. Okay, so I think there's a sort of positive and a negative outlook for the future. This theory is limited, I didn't say, but the Fukaya category only has a space of stability conditions if the first Chern class is 0. It's taken 10 years to prove that the space of stability conditions on the derived category of a threefold is not empty. We're way out of bounds of being able to prove it's contractible. But nonetheless, there are enough tractable examples to have given us some new phenomena, and there seem to be many new things that one can try. So I think this is kind of quite an exciting time to think about this circle of ideas. In particular, thinking about stability conditions is often bound up with thinking about mirror symmetry, and that's somehow a separately compelling endeavor. Okay, so thank you for your attention.
Perfect timing, even without the clock working. So, any questions?
So if you take the cotangent bundle of a surface, that's maybe even easier than the K3 surface. This diagram, this chain of maps you have from pi1 that ends in pi1 and has the stability condition, does that work perfectly in the case of the cotangent bundle of a surface?
Are you taking this as your symplectic manifold?
Yes, that's my symplectic manifold.
And an algebraic surface or
No, your surface.
my surface? Yeah. That actually turns out not to have an interesting Fukaya category. If you think about, okay, so it depends. If you take a real surface and you take its cotangent bundle, then the Fukaya category is basically chains on the based loop space. It's modules over that differential graded algebra. But that's cohomologically infinite, and I don't think anybody's really thought hard about computing spaces of stability conditions for cohomologically infinite categories. If you restrict to only looking at closed Lagrangians, there's only one object, and I'm not really sure that my guess is that that category is so simple that it doesn't actually admit a stability condition. So that turns out not to be the easiest class. Probably for very simple quivers, the categories that arise are strictly easier from this point of view.
Any other question? Okay, so let's thank the speaker again. Thank you.